Thank you for coming to this talk in the afternoon on the second day of the conference part of this whole Norwegian Developers Conference. It is really interesting to talk with people here. I am not a developer. I am a mathematician, and I use all kinds of tools from computer science and modern web development, et cetera, but only if I need to do something. So I'm here basically because I like to learn from people what you do, but also because data is everywhere. Like, I've talked with people here who do back-end stuff. Usually that's managing data, right? You do front-end stuff. Often it's providing some interface for data so that other folks in your company can look at what the metrics are for this or that, manage reports and analytics. So if data is everywhere and it's changing how everybody does their job, this topic might be of some interest to you, but it's also just for fun. I'll start with an overview of machine learning, actually, because that is the buzzword of the day, and because this topic of topological data analysis fits near machine learning, right? Even if you don't do machine learning, you've heard about it. There have been a lot of good talks here, DevOps for machine learning this morning, Damian Brady, and Bias in machine learning yesterday, Art Dohler. And there's a lot that machine learning can do for you and a lot that it is hyped to do that it can't actually do. So one of the things that I have found is that machine learning, people think you put in your data and you get out answers that are correct, however that happens. And that's just not true. And I want to differentiate this topological data analysis, this way of exploring data from machine learning, because you don't get an answer by putting in data. You get information. And so, although we'll talk a little bit about machine learning to put this in context, one of the messages that I have for folks who are curious about machine learning is that I think the future is not that the machines will just decide things for us, but that we will have machine-assisted human intelligence. And I'll show you what I mean in some of these examples. Machine-assisted human intelligence, not artificial intelligence to just solve all the problems in the world. So here's a really big top-down view of a few features in machine learning. So first of all, you've got to think about the kinds of data you have, structured data and unstructured data. Unstructured data, you can get blog posts, files of audio from people talking, people's video content, all kinds of stuff that is not easy to put into columns in a spreadsheet, for instance. And that's probably 80% of the data out there. That's what I've heard. And then there's structured data. You can put it into columns in a spreadsheet, in essence. It's easy to put into a structured database. And that's what we'll essentially concentrate on today, because it's a little bit easier to work with. Then after that big overview of structured data versus unstructured data, we zoom in on the structured, and we look at supervised versus unsupervised machine learning. So supervised machine learning is what a lot of you have encountered. For instance, you have a lot of historical data about good periods for your company's products and bad periods for your company's products. You have sales data, for instance, and you look at all the other factors that can go into that, and you make a model. Like, oh, if I change these things, then I will have better sales, potentially. Or you work backwards to say, why did I have bad sales this year? Maybe it's because of this. But you have some output that you're fitting a model to in supervised machine learning. Or you feed all these cat versus dog pictures on the internet, right? There are all these machine learning algorithms that are learning to recognize pictures, and they started by using labeled data. So you feed in 1,000 images of cats and dogs labeled by undergraduates who got paid $7 an hour in a work study to label images. Or these days, Facebook is taking all of your pictures of your friends that you have labeled with their names, and it is training on that data. So regression, classification, these are classic supervised machine learning techniques. And we know that the world does not have all kinds of high quality labeled data. And sometimes, in fact, you want to find patterns in your data that no one knows about yet. Like, sure, you can identify cats and dogs, but what are the features that you may never have thought of that you might want to discover in a data set? So that's where we go over to unsupervised learning, and then in really small letters in the bottom, data mining. Data mining is kind of an old-fashioned thing at this point, but it has never gone away. It's not the buzzword anymore. But data mining is this idea of getting insights from data in many different ways. And then unsupervised learning is about using a lot of particular techniques, whether it be eventually neural networks and things like that, or other tools like dimension reduction, singular value decomposition, and principal component analysis, or clustering, or manifold learning. So I'm not going to mention a lot of algorithm names for clustering, manifold learning, that sort of thing. I don't think that's the important part right now. But what I want you to think about is the shape of data. Some things are really linear systems. Like you can do a linear dimension reduction and just figure out like, oh yeah, if I want to look at tech stocks, then I just need to look at the prices of Microsoft, Amazon, Apple, Netflix, and Facebook, and then I will have essentially all the information about that small part of the sector. Like you can reduce a lot of things to a linear relationship, and in that case, we have linear algebra. You can do that. Sometimes you have clumpy data, so you can use unsupervised learning, for instance, for clustering, and you can discover that there are different groups in your data that are sort of disattached from each other, right? Here's something here, here's something here. Maybe I'm classifying the sizes of grains of wheat. Like I was looking at a data set recently that really just had information about sizes of grains of wheat, and you could see clearly that there were several different varieties just by using clustering. Okay, there's 3 kinds of wheat. Manifold learning, sometimes there's an underlying shape to what you have that lies in some space. So if you're looking, for instance, at a robotic arm and where it can go, it can only get certain places in space because it can't move everywhere. It's constrained by its angles. And then the topic today is topological data analysis, which is a little bit different than all of those things. And the reason is that topology does not care about distances. All the rest of these, they're looking for a structure in the geometry. Like you have a manifold in this space, you have clusters here. Topology is a little different because it doesn't care about distances per se, it only cares about relationships. And sometimes that's a good way to look at things. So distances, this is the classic picture for topology. A coffee cup and a donut are the same to a topologist because you can transform one from one to the other without ripping anything. You're not tearing any holes. You're just stretching. There's no gluing. There's no ripping. You're not changing some important features of the data that topologists care about, which is the number of holes, the relationships of all of these points to each other. So that's a good place to start. If you take only that away, then you probably know more about topology than the vast majority of people on this planet. But how do you do that with data? Like, how does that make sense? Data comes in lines in a spreadsheet or a CSV file. So I was raised as a pure mathematician, and there you have beautiful objects, idealized. You do not need to do any data processing. In computer graphics and stuff, you can use some of those ideas and discretize it. That's fine. Now you have a donut over there that's sort of discretized. You have points on its surface. But that is not how real data comes when you're doing data analysis. Instead, you have something more like this. This is the S&P 500 stocks over a period of years and how they are in relationship to each other. So that's a dimension reduction. I've got 500 stocks, but I squished it down to the two most important dimensions in terms of variance in their stock prices. That's not beautiful. Well, it's ggplot in R, but it's still not that great, right? How do you see any structure in that? I mean, I colored every stock by its sector, and you can kind of see there are globs of green on the top. I think that's like mineral and mining companies. And then there's like a cluster of financial stuff. But it doesn't separate nicely into clusters the way you think it should. So the idea here is that if we want to care about the shape, then we need to build a graph on the data and look at the rules then that the data obeys on that graph, essentially. So these are called simplices. Basically, you're going to connect the dots on your data. That's all. And once you have that graph structure, you can look at the properties of the graph. There's been a lot of social network analysis and graph stuff, but this is a little bit different because it looks at some of the higher dimensional components. So we really care about like when a piece in your point cloud is connected to like 5 other pieces as opposed to just one other piece. So like how many neighbors does every point have? How are they connected? And what I'm going to concentrate on today is how that can help you with visualization in particular. You can ask me about some of this other stuff too, but today I'm going to concentrate on visualization. It looks better on the screen, you know, than some of the time series stuff that we could do. So I think I'm going to start with a little bit of financial data, just to talk about some of the messy stuff that you can get into, and then I'll talk about some health data. And you should ask questions if you have questions along the way. And if you want afterwards, I have some slides about how you quantify this stuff for predictive modeling. But it's just not quite as pretty. So presumably you're here because you are interested in what developers are interested in. Either you're a dev or you just care about what devs do. So I gotta disclose what I use. There is a company called Ayazdi out in Palo Alto that is a great startup that does this stuff. They have a beautiful setup that's proprietary and I can't afford. So I don't use that. I use Python and I use R. I'm at a state university. So there are some really nice packages for Python and for R that help you both do the analysis and the visualization. There are some drawbacks, of course, to all of these things. I'll show you some of the good, the bad, and the ugly along the way. So for visualization, I want to tell you about an algorithm called Mapper, which is like the slogan at the top, slice, then cluster, then connect, is really the key. You have some huge data set, high dimensional. You want to see the structure of it somehow. You know it's not a good cluster sort of thing. It's not some robot arms locations. It's not an easy manifold structure. You don't know what's there. You want to do some basic unsupervised exploration, see what the data tells you. And so this mapper algorithm basically says, decide on your metrics, slice up your data, cluster on each slice, and then connect the clusters according to whether they're overlapping. So you're going to slice into overlapping pieces, cluster, use k-means, dbScan, whatever you want to use. Play with that. And here's a quote from the original paper that introduced this. That was not done by me. That's by all these folks. Gunnar Carlsson's at Stanford. I can't remember where his brother is. Michael Bejamo Johansson. Gurjit Singh, a few of these folks started this startup, Ayazdi, and then others are at places like Intel and stuff like that. But you see the idea here, like a hand, you can't do clustering on a hand and get much sensible stuff out of it. And it's also not just like the shape, the fact that it has 5 fingers really matters, right? So if you slice into these overlapping pieces, cluster, and then connect, you can get this skeleton on the bottom that tells you about the real structure of your data set. And it preserves these important features like there are fingers, there's also a palm. So somehow I like this technique. There's plenty of techniques to analyze your data, but I like this for certain kinds of high-dimensional data sets because it really gets you something in between continuous and discrete. It really distills down the structure of your data to some sort of shape that then you can ask questions about. So let's see. I was looking recently at the MSCI IFA. It is an index of like 700 stocks from Europe, Asia, and the Far East. And somehow I can't get HTML to embed in PowerPoint. So if you look at these 700 stocks, you can look at the correlations between their returns. And you can make a graph. Like I will draw edges only between stocks that are highly correlated. Like they're moving together over time. Let's draw a graph. And this is trying to be too clever for its own good. This is using D3. And if you hover, it'll light up that part of the graph. And you can see that it's having a little trouble. It's also a 700 node graph, so it's kind of big. But you can see that this has what they call the hairball problem. Like when it lights up, you can see that it's just a ball of stuff. You can't understand anything from it. It just is an enormous mess. And so what I want to show you is that with Grapher, ignore the stuff on the left. I was trying to color by sector and stuff like that, and it's not quite displaying right. But this is the same data organized in a different way. So this mapper algorithm, I took my 700 stocks in some space and I sliced it up, looking at correlation between them as my metric, and clustered. And then you can see that there's much, like this is one set of stocks, a ton of Hong Kong stocks, like primarily Asian stocks here. And then this is another set of stocks, really clustered together. As you go over here, there's more European stocks. So I think, although D3 is not being my friend here in this large context, this is a much more refined structure. And you can look at each of these clusters by themselves and say, why are these connected? Why are these connected? What do these have in common? And so what we're working on right now is analyzing, by company, by country, by sector, all of this kind of information, by fundamental information when it comes to stocks, what this structure comes from. And the thing that I'm particularly interested in for this is the structure over time as we have crashes and recoveries in the economy, right? So that's 700 stocks. I used network D3. This is what it looks like in iGraph in R. It is not pretty, I gotta say. iGraph is a great package, but it's ugly. So I haven't done all the analysis that I want to do on this particular set of 700 stocks, but you can see that you get a structure out of Mapper that is useful, potentially. I'll show you a more cleaned up example. This is something we've been working on for a while. I've got a bunch of colleagues in the School of Public Health at the U, It seems like when I've talked a little bit about this other places, there are tons of people in healthcare, for instance, who are trying to do personalized medicine and stuff like that. You try to take data from people's health records, from their devices, all that sort of thing, and figure out how you can intervene to prevent problems later. This is a little bit more old school. It's a survey that started in 1997. You filled it out with a pencil and all that originally. And it started by surveying 4,000 high school students in the Twin Cities about their eating habits, about their activity, their exercise levels, how their parents felt about weight and meal times and things like this. Like an incredible amount of data. It is structured, so that's nice, but it's got all this psychological, demographic, and food data. And the thing that I'm working on with this team in the School of Public Health is something called the dieting paradox. So we know that obesity is a problem in America because it leads to health problems, right? And so you should tell everyone to diet, and then they'll lose weight, and then we won't have health problems, right? Well, that has not worked very well over the years, and there might be some confusion of correlation and causation here. So it has not actually been proven, for instance, that obesity is the result rather than the cause, or the cause rather than the result of some of these problems. So one way to try to deal with some of these public health problems is to go back and look at people's actual behavior. Because what like medical professionals say when they say diet and exercise, well, what do teenagers actually do? And what do teenagers actually think? You know, think back to when you were a teenager. You were probably just an average kid, right? Most people are basically average. But your ideas about what you should be or shouldn't be influence your actions. And your ideas about what you should or shouldn't be, especially with respect to health and exercise and food, may not be reflective of reality, right? So, what do teenagers actually do? Some of them eat more vegetables. Some of them just don't eat breakfast. Some of them do a South Beach diet. Some of them, these days, go paleo or whatever. Some do the blood type diet. Some of them, anyone heard of this like lemon juice cleanse where you only drink water with lemon juice and cayenne pepper? See, there's always a few people who not. Like maybe you haven't done it, but that's what people do, and that is not what your doctor is telling you to do when they are telling you to do diet and exercise, right? So the observed problem on a public health level with telling people to diet is that for a substantial percentage of the population, it leads to bad outcomes, weight gain, and mental health problems. For some people, it works really well. Why does it work for some people, and why does it actually make some people's lives worse? That's what we're trying to figure out. It's a big goal, but let's look at our data. We have these 4,000 students who filled out all this stuff, and linear methods just fail. You can do all the principal component analysis and projection you want, and I will write about that a little bit. But the problem with looking at the people side of things is that most people are average. And you just can't tell that much. It's a very high-dimensional data set, and you just can't differentiate between people by taking a linear slice of your data on the left. And on the right, I was looking here at doing a singular value decomposition on weight control behaviors, like unhealthy weight control behaviors. And it picks out fasting and then use of laxatives to lose weight, which are not that common. But the reason it picks those out is that they're the highest variance behaviors. They're the ones where you have the highest variance in the population because they're rare. So that's also not useful. from a public health perspective? Why are you going to just pick on a few rare things when we're trying to look at the big picture? So this is where TDA comes in, and I think it's been really useful here. We haven't written the paper yet, but we're working on it. So I have a 38-dimensional point cloud with 4,000 points in it. Those 4,000 people and 38 demographic, psychological, psychosocial dimensions. So you decide how to measure distance. There's a couple of ways to do it. You slice, you cluster, you draw edges, and you get some real structure. So this is only looking at boys. I have the slides for girls too if you want afterwards. But I think looking at teenagers, this is kind of instructive. There are 2,377 unique boys in this sample. I'm sliced it into the data into 16 pieces, do the clustering, draw lines between them if there's overlap. Unfortunately, I think I need to darken the lines here because there are lines, maybe you can see them, all along here. So it's like there's a big backbone here that's connected, and then there's a hole here. And then I colored it by percentile BMI. So red is higher percentile BMI, and green is lower percentile BMI here. And that's for each cluster. And this visualization right here, you see that there's a structure in this data. Like, I didn't, okay. There are a lot of variables I didn't include here. BMI is one of them, but it's one of 38. And still there's this high BMI area, medium BMI next to it, low BMI on the other end. So that's interesting. Does it really matter? Does this really give us anything? So let's look at some behavioral variables. This is actually whether you're trying to gain or lose weight was one of the survey questions. And I think the naive public health approach at this point is like, oh, everyone's trying to lose weight, right? But that's not true. For instance, and this is one reason I bring up teenage boys, not all teenage boys are trying to lose weight. Many are trying to gain weight. So this is coloring by the proportion of boys who want to gain weight. So in this higher BMI group, boys don't want to gain weight. In the lower BMI group, there are some clusters in particular where like kids really are trying to gain weight. And then I think here's a trying to gain weight cluster as well, but I think the motivations for trying to gain weight here and here are different. So there's like the boys who are pretty low weight and are trying to gain weight just because that's what they want to do. And then there's the kids in sports who are like, I need to make a certain weight class or something like that. And you can start to see this if you go a little further. This is boys trying to lose weight. Over here, boys are trying to lose weight, and no one else is really trying to lose weight. So that's not really the focus we should have, maybe. And then if we look at dieting frequency in guys, only a small percentage of these guys diet to lose weight, right? So there are other behavioral variables at play. This one's confirmed binge eating disorder. And you can see that it's very rare except for 2 groups. And then we can go back, dig into the data, and wonder why, like here on the lower end, it makes sense to me that there's binge eating disorder confirmed in this group because they're a group of guys who are dieting a lot. And those behaviors are correlated in the literature. But why up here? These guys aren't dieting. So that's something to figure out. This is body dissatisfaction. And look, it's not the high BMI guys who are the most dissatisfied. It's the low BMI guys. And then you can go to most satisfied. these guys are most satisfied with their bodies. And they were just in the middle. And then you go to exercising a lot. Oh, the guys who exercise more than 16 hours a week also tend to be the most satisfied. Whoa, this is interesting. And then people who exercise less than 6 hours a week. So you can go through all your variables and just light up the hot spots and try to figure out, using domain expertise, what's going on. So in this particular setup, what we did was, I sat down with some dietitians, nutritionists, public health types, and just eyeballed it, honestly. Like, where would you draw the lines for this group versus this group? Let's go analyze it. This is not machine learning at this point. This is machine-aided human intelligence, right? We're using this for feature discovery. We're trying to pick out what in the data might be a driver and how we can set up a model after that. So, and just to lend some credence to this, even though we did eyeball the groups, they're statistically different, significantly different. That's kind of fun. So there's a little bit of just playing with the data. This is almost like exploratory data analysis at this point. And I think that this is useful because it allows you to disentangle the correlations and in various groups. If you just look at averages of your data, you do not see the shape. You just see one number, right? Here, on the other hand, you can see that on a public health level, it's the people who are winning are a particular group of young men who don't exercise very much, don't think weight's important, don't stress about it, and don't do anything, like, at all. They don't do the good things, they don't do the bad things, they don't have any of those problems. And yet, it's the very active kids, of course, do very well as well. But it seems that maybe caring too much actually can be a problem. Don't take any public health advice from me, but just look at the data. It's interesting. So these are statistically significant groups. And this is, I think, where we then take these insights back, the feature discovery, put them into traditional statistical models or agent-based modeling. That's one thing that we're looking at. I don't know if you've heard about that. Just to model what will happen in the future. So who knows the difference between machine learning and modeling? So machine learning, you put in your data and you do some learning on it, and maybe it's a neural network and you cannot explain anything about how it works, but it gives you an answer, right? You need tons of data to train that neural network, and then it can do a very good job sometimes, right? Modeling, on the other hand, F equals ma, right? Force equals mass times acceleration. That's a model. Did you need tons of data to figure that out? People did use data to figure it out, but at some point, you can create a model from domain expertise without having data. You used data to test your model. And so this is part of a big cycle in machine learning. Use machine learning to discover features, bring the features back, create a model, then test your model, and iterate through that process over time. So at this point, I will ask you, which direction do you want to go? Do you want to talk about how to make this quantitative for modeling, or do you want to look at more pictures? Pictures. Let's see. Let's look at the girls' behavioral stuff for the moment. So where would you put the groups here? What's different and what's the same? Okay, that one told you my groups, although it's upside down. So this is girls and percentile BMI. So there's a lower BMI backbone again and a higher BMI part of the backbone. And then this end is different than for girls and guys, somehow to me. This is percentage of girls trying to gain weight. Like, girls in high school are not trying to gain weight, by and large. There's like 20 who are in my sample. Trying to lose weight, well, that's a lot. And in particular at this end. So I think what's interesting, this is the high dieting frequency end as well. And this is the eating disorders end. And this is the never exercising, less than 4 hours a week. And this is exercising 13 hours a week or more. So I think what's interesting is that girls and guys are really differentiated by the way that exercise versus gaining weight plays into what they think. This is a graph of depression. So unfortunately, dieting frequency and depression, like perfectly correlated in girls. So if you split them up, you can really see a different pattern of movement for girls. If you are, just look at the diets per year column, if you can see that. The high dieting group is like 15 or more diets a year. And then there's, again, the I don't exercise and I don't do anything and I do okay group at less than 1 diet a year. Like, there's a huge heterogeneity in how people approach all of this stuff, right? And I think it's very useful to be able to look at it on a continuum, not just in averages, in population numbers. You got to be able to pick out the different structures. This is one cool thing. I took those same people, carried them forward 15 years, and the differences persist. And people are basically doing pretty similar things as they did in high school. Like, our habits are set in many ways when we're young. So, any questions or anything you want to go back to in there?
Could you explain more about how you use a graph? Because I haven't seen you teach this topographical approach. It's not in any of the classes I've taken on this. It's pretty unique. It definitely differentiates things in unique ways. So.
Yeah, it's unfortunately, it's because it's not machine learning per se. It's not covered in any of those classes, but it's applied math, not pure math. So it's not taught in topology classes either. So it's going to take a while to make it into the curriculum that you need for any graduation requirements. And there are some great tutorials online, but you have to look for them. You have to know exactly, the name that you're looking for. So let's go back to this picture for a minute. Here is the hand. To go into a little bit more detail, the color on there is actually useful. The red to blue on the hand, that's some metric that you put on, and you've got to have some filter function. So you choose some sort of function, whether it's low correlation to high correlation, or if you have some average value that you're interested in of something, you pick a metric like that and you put a filter on it and you slice according to that. So I've also used, for instance, standard deviation from the mean. That's a good metric to slice along. Here it's just right to left, which is pretty nice. And so you take whatever filter function you have, here, right to left, and you choose the number of intervals along there that you want. So for a lot of the images that you saw for the eating stuff, that was 16 intervals. Just 16 evenly spaced intervals along whatever metric you chose. And you slice up the data and just look at each alone. So you look at one slice alone, like here, 1, 2, 3, 4, 4 different clusters on this slice, which is why you get 1, 2, 3, 4, 4 different nodes. You notice that this hand is longer than this one, and that's because each slice overlaps with each other slice. So you have to have overlap so that you can draw the connecting parts. So here, 1, 2, 3, 3 clusters. Here, 4 clusters. These two have overlap. So you draw this line. These two have overlap, so you draw this edge, and so on. And everything, for instance, in here, overlaps with the one cluster that's yellow. So that's how you get the 4 edges coming to that one yellow spot. There is a lot of art rather than science at this point to some of this. Like that's a well-developed algorithm, but you can use whatever clustering algorithm you want within it. So it shouldn't change your results too much in my experience, but you can use dbScan or k-means. Yeah, there's a couple other that are easy to use. So this is all implemented in something like it's the mapper algorithm, but it's implemented in both R and in Python under that name. And there's an effort to build a whole library that brings topological methods to in a scikit-learn kind of style. So you can use scikit TDA. That's what they're calling it. So it's not machine learning. So it's not scikit-learn, but scikit TDA. My advice is R, easy to get up and running very quickly. Python gives you ultimate control, of course. That's the trade-off. Yeah, any other questions? So I dropped a lot of things actually when I was doing this clustering. So I'll bring this picture back. So when I was looking at this, I have a huge file, like thousands of columns of data. But what I did to create this is I dropped race, citizenship, socioeconomic status. I kept gender. That's actually really useful to differentiate by in this case. And I then only kept these psychological variables, exercise-related variables, and caloric intake, things like that. So I tried to drop as much as I could to build on only a subset of data so that we could test these other traits against it and see if there's any value to it, predictive value, essentially. So this is a hard thing, I think, in TDA, and this is, again, going back to that machine-assisted human intelligence. You have to decide what you think will show you this structure and try it there. And then you need some way of testing it. You can find patterns in anything if you just apply the right algorithms or enough of them. So here, we wanted to really look at behavioral and psychological variables only and see then if they could predict, essentially, some of these other outcomes. So you have to decide what's your input and what you want to test it against as an output. And I don't think I included age, for instance, but there are some age differences in the groups. So there's it's showing some value in picking out predictive factors, but you can't put those in if you want to predict them. right? Like, so that's part of the back and forth that you need to do with your domain expert. Like, it's the public health people who help decide what to put in and what to try to predict. They've done some really cool analysis with genetic data in particular. So there are a bunch of papers that look at diabetes, for instance. And what they do is they take only clinical presentations of people coming in with problems with their diabetes. Only clinical stuff, like, oh, I have an eye problem because of my diabetes. Oh, I'm experiencing neuropathy because of my diabetes. I have heart problems, and I have diabetes. And they did TDA only on those clinical presentations, and then they overlaid people's genetic information on it in the study, and you can see that there are different genes involved in certain outcomes. So that's pretty cool, like working backwards from the clinical presentation to the genes that maybe have something to do with it. So you have to decide what you want your input to be and what you want to test it against, essentially, as an output. Other questions? I'm available to chat afterwards too, if you want to chat. So I have many pictures, and you should just let me know if you want to look at them. So, question. I have to put up my funding acknowledgements, so.
So if we, per se, wanted to play with topology and things like this, where would you suggest we get a large amount of random data that we could play with?
Oh, this is an interesting question. So, first of all, I will say that I have a couple Jupyter notebooks and things like that, and in fact, an R notebook on mybinder.org. I don't know if you've ever heard of this, so that you could play with it like now without installing everything. Those are set up, though, with fake data that's small, so that you can just play with it without challenging your computational capacities. So one really nice set to try first is actually the Wisconsin breast cancer set. So this is a classic machine learning set that's widely available, freely available, from the UCI machine learning repository, for instance. So if you look up Wisconsin breast cancer, UCI machine learning, it'll come up. And basically what that data set has is a lot of features of a biopsy of a tumor. So it's got tumor size and like how furry the edge is. There's a technical term for that. But then it also it's a labeled set. It has whether the tumor is benign or malignant. And you can do TDA on the tumor characteristics, leaving off the classification, of course. And you will see that there's a real striking pattern there. It was one of the first test cases that they used sort of as a proof of concept, and it's worked really well. I think health data works really well. I've done it with some of these diabetes data sets that are available freely. You can see type 1 diabetes, type 2 diabetes, and normal, like as 3 arms of a Y, basically. So that's kind of cool. So health data that's freely available is where I'd go first. But I will say that's one of the reasons I did all this stock market stuff. That's freely available from Yahoo Finance. So it's not always good data, but it's free. So. Yeah, I will be sharing a lot of this on my GitHub page, so you can always check out code examples there. Yeah, well, thank you. And I think it's time for afternoon tea now.